Hello. Today we are starting again to work on this unobscured. No, these are obscured. See, I found a mistake. Unobscured quasars or dusty quasars. We are gonna make one sentence contribution. You will see. Right. So it's obscured quasars. We're studying, investigating with this data. And let me launch my timer because I want to do these tutorials in about 20 minutes. So I have this video tutorial part 3, but we'll see really if it's beyond 20 minutes, then I will stop and record and the rest of it in another video tutorial. So that we don't need a way. All right. So today we are doing this video tutorial part 3. And what we will do, the main goal is to create combined science image without cosmic rays. So what are we doing today? As I said, the main point is to combine 3 science images, 3 exposures into just one. And the main reason is to get rid of cosmic ray hits. And some other points here, we will continue using the terminal environment. Um, Maybe there isn't really a script. Well, writing scripts in general, I will say, writing light scripts. And there will be introduction to the IRAF environment, which is maybe obsolete. I don't know, but that's what I used. And I think it's a good tool to use. I have also used Python, but um, you can give me your opinion. Remember, in this column, I track um, what I'm doing step by step and my thoughts. And in this column, I write research notes, which go to the more traditional research notes of the uh, project. So, yes, we will continue to use a terminal environment. We will write some light scripts, get the flavor of what IRAF environment is. And I wanted to note that working in IRAF and in terminal in this environment might not be so intuitive. The key commands might work. I'm just checking if I'm recording. I'm recording. Okay, for example, the delete button or navigation buttons might behave not in a ways that you expected, but this can be quickly learned. I also want to say that when you work in science, there are many solutions to a problem. So what I'm trying to do, manipulating files and manipulating images, it can be done in many different programs. I'm using IRAF, but you can also use, for example, Python. Um, if you want to check the header, You can use all IRAF, you can use Python. AstroPy tools exist for that. You can even use Terminal, or you can use QFits View, which I like. For example, we can open, um, I will delete these ones I don't need. I was testing some things. Try to be correct things, not incorrect things. Yeah. Okay, so each fits file also has header, and the header gives you information, for example, about the instrument. You can look at it through DS9. Here, file header, display header, or click here's a header, and it can give you the date, guess different information, the date of the observation, size of the image, instrument setup, observation information, etc., etc. What's on your x-axis, what's on your y-axis. You can also use QFits View, and what I like about QFits View is that you can display the header and then you can search. Let's say I want to know what is the gain. It's not here. Read noise, no. Exposure, no. Mine are wrong. Was in a wrong extension. Here is the gain, but let's say if you have a very long header, then you can find what you're looking for easier. So here, each extension has a header. We are going to need later gain, rate noise parameters, the bias sec parameter. Okay. So I find this searching by typing in QFits View header environment very useful. For example, especially when I use ISO data, the headers are very long. Remember, yeah, if you are using Python, then you have to keep in mind that what fits reports, the counts, they start from 1. So Python starts counting from 0. You have to take that into account. Also, you have to make sure that what fits image tells you is x-axis, y-axis, how it corresponds to your Python grid rows and columns. Just make sure that you are correctly translating between the two. So iRef is convenient. It has the same kind of language as fits. What did I, where? So in research notes, we can record that we are working on this Quasar 103 from one night. I can write. Today is February 5, and I am focusing on quasar 103. Okay, this I will do later. This we are gonna do today. Okay, we are done with number one, row number one. Is there? Okay, what is an image? When you look at an image, I'll open it in DS9. It's a two-dimensional paradigm. It's a two-dimensional image, X and Y axis. It's a grid of pixels. Each pixel is identified by position. You have a certain number of pixels in X direction, so the number of pixels in your Y direction. So some of the pixels have a bright value. Here it's white. Some of the pixel brightness is low. I think here, let me, so if I'm here, for example, you can kind of zoom and start seeing these individual pixels. And you can even, I believe, how was it? No, pixel table. Yes. You can get the values in your pixel table. See, as I move the cursor, um, in blue, the numbers are changing, showing the coordinates, X and Y coordinates of the pixel, and the numbers in black shows the pixel values here. And the one in red is, I guess, the center. Let's say this one should be very bright. Is it? This should be less dark. Let's go to a bright part like here. Then darker part here should be lower values. Okay. So yeah, it's a two-dimensional image. Is a pixel grid. It has pixels in two directions. Each pixel has a location described by two coordinates, row and column, and each pixel in an image has a value associated with it, showing how bright it is. It's a flux indicator for us in astronomy. So one question is, what are the dimensions of Alphonse image? How many pixels are there on each axis? So I can consult the header, for example. And here I have lengths of data axis 1. It has 2,148 pixels. And length of data axis 2 has also a similar number of pixels. And so you can find that information in the header. Or you can go to the very last pixel and get it that way. It's so many ways to get it. You can also do it in Python, of course. Okay, we are done with part 2 of this tutorial. What we did last time, and let's close this. What did we do in the past? In the past, the aim of this project is to reduce and analyze spectroscopy data from the Node telescope. Yes, so that's the goal of this project, and it is an open science tutorial where I hope to demystify science project work to the general public. I think I posted on YouTube. What did we do last time? In tutorial 1, we downloaded the data from the Node archive. In tutorial 2, we decided to focus on observations just from one night and sifted through the files for that night. So what are we trying to do now? Yes. Thank you, God, let's start with a prayer. Thank you, God, for giving us opportunity to work on this exciting project. It's Thank you that the data came through well and we were able to get these observations done. Thank you for giving us wisdom to guide us. In the name of Jesus, amen. Review the summary of the procedure log. Okay. So in this procedure, I wrote when I write these long procedures, I try to do summaries of each point and summary of the whole procedure. So what we are trying to do, actually, we are in a way losing information because it's a 2D image. And from this 2D image, we are trying to collapse the information for that object into a 1D spectrum. So all of the reduction steps are performed using standard IRAF procedures, and they are well documented. For each step, you can, I will post resources, but you can read up more on their documentation. So first, the frames were inspected and organized before, maybe I'll shoot. Okay, let it be in a past tense. First, the frames are inspected and organized before starting the reduction by type. And we have done that. We have done that in a past tutorial. Now we're entering this second point where if a target had more than one exposures, these exposures are combined with IM combined so that the cosmic rays are dealt with. That's why we take, so this is what we are working on now. And that's what we take. That's why we take multiple exposures. I'll put it in yellow, or maybe I should put it more orange. All right. Later, we will do these other steps. Mhm. So we highlighted which steps we are working on today. Is there anything I wanted to say? Yes. Let's show. Here are our science exposures, which can be also seen in the EON report for Quasar 103. This is EON for 18. Quasar 103 is here. Our Quasar 103 had actually 4 science exposures, but three of them 1800-second exposure, but one of them was very short. And actually we are gonna make a note of that in our research notes. Describes the science exposures. Maybe I should. For Quasar 103, 4 exposures were obtained, but only 3 had 1800-second exposure time. The last exposure was very short and we will pretty much discard it. Will not be used at this point. Okay. So we're gonna start getting the flavor of what working in IRAF is. We will be checking after each step to make sure that the reduction steps are working as expected. We will open before and after in DS9 to compare those images. And we will have to write a summary of what we did after each step if needed and record each decision. All right. So I'm getting close to my 20 minutes. I will finish this 4 and 5, and then we will do um, another follow-up video. So information on procedures and working flow. What do I mean by that? Is that it is good to learn from other people. For example, my NASA mentor was very good at explaining how people think, how procedures are done, ins and outs, practical advice. She was very good at explaining this. But on the other hand, one of my PhD supervisors was extremely hands off. So I had to do a lot of footwork myself to get information. And a lot of that information is out there, but you don't know unless you've worked on it before where to get it. So you can, if it is not explained to you by your supervisor or by your teacher, you can use documentation, textbooks, your peers, websites, uh, websites associated with the instrument that you are working with, the company or the project that you're working with. I shouldn't say company, I should say the institute that you're working with. You can look at manuals, there are technical guidebook publications, even on data reduction. You can read other people's papers, the methodology section, to see maybe they have given um, more details in their papers. Usually papers are succinct, but some people are very good at writing clear methodology sections. And I would say if you see a paper that has similar methodology and you're not sure about a step, go ahead and email the correspondent author with your question on how they did it. I've done it several times, and usually I get back a good answer. Um, Also, when you learn about other people's work process, this might give you ideas how to improve your own. For example, I did a coding meetup in Helsinki, and I learned there from a chemistry professor who was trying to become a data scientist, how to organize my functions or how to organize my coding files, because I learned coding on my own, kind of alone in the desert, um, alone in this Nordic tundra. So it was nice to hear how another person was organizing their coding files. And he suggested to put all of the functions into a single file and then call that file, the function within that file in your code. I'll show you um, in a minute. And from my husband, he's a very talented person. He's an artist and graphic and is good in design and computer programming. So this concept of iterations, and he's a good writer too. So when I create several versions, updated versions of a written document, a code document, or anything, I use his kind of suggestion of naming them IO1, iteration 1, iteration 2, iterations 3, so etc. to keep track. So two things I will show you um, before going further. One, the coding. Um, where is it here? Okay, if I have, let's say, a project, in this project, I'm working on um, some Hawkeye data. Hawkeye is an instrument uh, operated by ESA, European Southern Observatory. So there I wanted to show you that I wrote Python programs in order to sort through files, and I even named them that way. Let's see if I can make it bigger. No, organize files to get the darks, organize files to get flats, the read gain. There were more than 200 files associated with the observation. So there was no way I could do manual tables like we did. Um, Instead, I used Python and AstroPy tools in order to, for example, check the coherence of twilights or, update headers or whatever I had to do. This is an example. Uh, in this program, I found all the darks, and darks are part of the calibrations. We also have darks with alphas. So, um, I found whatever keywords I needed, and then I wrote a loop-de-loop, in order to go and find the darks, and they had to be coherent, with the same date of the observation, same whatever was needed, not just some random darks. And I usually like to, if I'm unfamiliar with certain data set, to print things out so I can also visually see and visually check and what's going on there. So this is one example, and I wonder if I can do another example to show you the function. Am I? Okay, so this is another project where I'm working with gamma spectroscopic survey data, and these are all my different code files. See, for example, this is IO1, then IO2. So IO1, IO2, different versions of the IO1, O2, O3, O4. So I have a record of my changes. But in this set of coding files, I have uh, one file that lists of all my functions. So how to calculate the spatial separation, moving spatial separation between two objects, how to get the radius of a volume, how to get the median, how to join tables, how to add a property to a table, or how to get a luminosity function. So I put them all there and then call them. Let's see if I have anything that I called. Maybe here, I'm not sure. Okay, from functions gamma import add property. So and then I call from that file whatever functions that I need. And usually I reuse a lot the functions um, within the same project, especially. So we covered all of this, and I can color this green. I don't know, should I go forward or make another? Let's go forward because my kids are coming soon, so I don't have time to do another video. So it's going to be a long video. Um, what were the changes that I made offline that I didn't show you live? I studied and wrote the tutorial steps to do just to keep them organized more, a little bit more. but we are doing them really together. I quickly did some tests to make sure my iRAF is working and stuff because it's on a new computer. And then I reformatted and clarified some of the procedure log instructions. So this is my procedures that I'm updating on how to do alpha spectroscopy for this type of data. And I also created a directory for code. We had directory for observing proposal, for our data, files, and now I have also for code because I might need to save some things there. So this is covered. We move forward. So we have to check to make sure, did I, do I have, okay. Do I, I'm just recording the working directory for this data in my research notes. That's important. Is there anything else that I should record from everything that I said? Ah, we have to write that we are using, we are using standard IRAF procedures, knowledge IRAF for data reduction. And I can put that into the paper. We get one more paper sentence. No, into the paper. And put it in here somewhere. Noise acknowledgements. Okay. We'll see if we need to write. We can write. Let me see, somewhere in conclusions, acknowledgements. In the paper, we can make a section. Maybe it will be an appendix. I don't know. But right now it's a section notes on individual quasar fields. And we can do subsection QSO 103. And we can write there. Well, for now, I will write as a comment for exposures were taken, but only 3 used because the last one was very short duration, 1 minute. And here we can say that we can describe more observations. Each quasar field was observed 1800 in 3 exposures of 18-second duration each, 30 minutes. Okay. Okay. So we're making notes on reduction. So we are making little additions here and there as we go. Okay. It's done. Check that I'm using homogeneous data. Yes, so we have to check that we are using homogeneous data. One way to do it is just to look, because these are such clear observations at the end of night report. So what am I checking? First, that it's the same chrism. Here's my QSO 103. Science. Is it the same chrism? Yes. Number 7, number 7, number 7. It's the same chrism. That it's the same size of data. Size of data is the same. That it's in the same night. It's in the same night. That it is the same slit. 1.3 and same PA. Do we have? Anyway, it is the same. I know, same slit, same readout time. Oh, good. So now we can answer the question. It was the question we had last time. Why are there two standard star exposures? What happened? What happened is we had these standard stars, but you can see that they are observed in different slits. So we have to be careful and make a decision which one to use. Uh, different slits. And then now moving forward, we record. Did we do that? Let's put a check mark on. And then I highlight it. Okay. This is today. Art. Check that you're using homogeneous data. We did this. I just put in there where readout times are explained on ALPHOSC. And also from the header, we need to record these data parameters of the observation of the instrument setup. And I already recorded it, but I will show you where I got it from. So it's from the header. We can open with, let's say, Cupid's view. And I think we looked at it earlier, but display header. And here you can see the gain is recorded, the read noise is recorded, and bias sec is also recorded. This is all done. Okay, so now we need to do our main goal. Now we can do our main goal, which is to combine the images and produce the single combined science image of those three science exposures in order to get rid of the cosmic rays. But again, before we go forward, I need to show you the IRAF. I'm not going to tell you how to install it. I'll post a link to IRAF documentation for your exploration. But we are going to quickly follow these steps. Okay, once you have the setup, once you set up the IRAF, I already have the IRAF. Maybe I put it in a to-do. So we have to go and check the IRAF is like a tool, a software. I can go and check the login CL of my IRAF. Okay, and make sure these are all marked. maybe we can do formatting. Set standard image. It's uncommented, and I put the correct value in there. So we are just setting settings for IRAF correctly for our reduction. Second one, I did this line set, and I did this to fits. Okay, this is that. And then from terminal window, we launch DS9, and I think this. So I'm on a new computer. Some of the commands are not exactly the same. Let's clear this. Do I have DS9 open now? So here's my terminal window. And what I want to do is launch my DS9 from terminal. So I'm just following these instructions. Enter. It should appear. Here's my DS9 window. So this is done. And then on this computer, I don't have a graphic X terminal, so I can only use Xterm, which is okay for today's step, but I'll have to resolve this problem for next steps where we need the graphic capabilities of the Xterm. So here we use this. Okay, this is my Xterm window, and I think I don't need this anymore. And this is also done. In Xterm video, change directory to working directory if not already there. What is my working directory? I can check. It's not. So I will have to go here. Here's my working directory. Hmm. So instead of Control C, Control V, I highlighted this, what I wanted to, highlighting it is kind of like copying. And then I pressed the middle button of my mouse, which pasted it here. So if I do Control V, in here, it prints some weird characters. So it just, some of the key commands are different. So now I'm in the correct directory. And here are my files in that directory. Now I can launch IRAF, and the IRAF program is launched by typing CL, and then I have to input my package environments, the optical, image reduction, IM red, CCD reduction, CCD red. So this is the setup for IRAF, green, and I have to set more parameters in SpecFold. In that instrument, I'm using SpecFold. The image is real, and then I have to check to make sure that bisect are, I don't know, intrinsic will update here too. Hold on. I wrote it wrong. It's 53 2098 to 2041. Now it's correct. Let's double check. Check, 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 check. All right. It was from the header and trim section I have here. We can put it into the video tutorial notes for you to check out later. I'm gonna skip some points which are not needed. And now, before we combine the images, we have to tweak something about our feeds files associated with each exposure. And this is from a tip from my not observational course at University of Turku. So we keep only for convenience. I should write here that this is for convenience. We will keep only one extension of the feeds files that is needed, that has the needed image for that we need. So if I go back to my working directory, so this is a feeds file, and I think it's best viewed with qfeeds view. It has two extensions. I only need the image extension. This one has the pixels of the quasar field image and the brightness recorded in it. I only need this one. You can call it by putting extension ID and extension index after the name of the file. But here we'll just, we never have to use this primary extension. So we, for convenience, will change it and make a copy of for all files to only have this image that we need for our work. Okay. So how to do this? You can type terminal commands in IRAF preceded by an exclamation point, or you can do in terminal as well. And I'll do this in terminal. So here are all, no, I'm in the wrong one. I have to go first to my working directory. And then to make sure, okay, these are all my files. I have a text file, never mind that. So we will put all our feeds files into a list. And we'll call it one list of night files dot list. List of night files dot list. I like to label, put into the name of files what they are. If it's a list, it's a list. If it's a table, it's somewhere right there that's a table. If it's a figure, I write that it's a figure. So I also like numbering my files. So my file numbers, the name, each file name has a number. Or I try to and it grows as a procedure gets longer and longer. So if I'm tracking back, I know that this file was created earlier in a reduction than this other file. Okay. Um, we can visualize now this created file. Here it is in Sublime. And I think we can. So we don't want to do maybe LaTeX because right now it's just the simple plain text, but the commands, I don't know which one is a good one. Can be maybe I do Python. Let's see. So these are the names of the files, and I need to change them. First of all, we'll get rid of this and put that we need extension 1. See, when you change the syntax type in Sublime, it gives you colors. This is my command. Oh well. And then I can copy this table. And I think extension 1 or X1 is a good name, right? For this. And I will save it. I tried to make this a very descriptive title, but for mine, I would probably use 1 or up to 3 words. So here it's a file to which gives a command to make a list with first extensions only. Extension 1 only. Press index 1 only for each file. So we copy the original extension 1 for each file and name it as the name of that file .ext1. Okay, and because I'm copy is a command of IRAF, so we have .cl at the end, so it knows how to read it. But see, I don't like how it looks. Let's find maybe C. No syntax, maybe Python. It was LaTeX. Maybe it is what it is. Okay, well, anyway. Copy is a weird command, but the major languages have their own commands, their own keywords, and those can be highlighted in different colors in Sublime to have more visual organization. Okay, this is done, it's saved, and now we will go back to our IRAF and pass it to IRAF with this command cat, which is going to read it and pipe it through IRAF. Okay, see, cat and the pipe. This is our list of commands for all files. You can also type each command on the command line, but then you might make mistakes. Okay, it's showing what it's doing. And we can check, for example, in this case, now how many extensions there are. Right. There's just one. All right. Check the results, how many extensions are in a random case. Update research notes. Do we have to write anything? Maybe I will just write that I am uh, finished step up to step 4 of the office procedure. My husband calling. I'm gonna stop. James? Okay, sure. Bye. Gonna pause. Where was I? Okay, we did create those, and now the final step. Let's just mark it done. I did this. File fits and zero extensions I did. We had 2 extensions. We need the one labeled 1. It's one index 1. It's index 1. We did this step and we did it and we executed it. IRAF. We checked what we need to update in research notes, and you'll see we don't need to. Now, the last step, our crown achievement, is to create combined image, which will allow us to get rid of cosmic rays. And my kids are already at home, so I better wrap it up. So in IRAF, we just have to execute this command. Let's double check. 61, 62, 63. Combine setting is set to median and rejection algorithm is CR reject. The rate noise and gain values came from the header, and this is what it did. And it combined these 3 images into the final image QSO 103. Our output image is QSO 103. It's a combined image. So let's check the results. We'll inspect the output image. We'll see if it's free of cosmic ray hits and compare to individual exposures. So our 61, 62, and we'll change the scale to 6 scale. 3, and also just to show 64. And we will go ahead and fit each image. And then our combined image is QSO 103, which is here. All right, on the top panel are the 3 exposures of 1800 seconds, and you can see that they have these little specks and even lines. Look at this line, something was flying through, which uh, are the basically cosmic threat hits on our CCD in each exposure. But when you median combine it, you get a much cleaner image, which is depicted here. There are other problems or other things that need to be accounted for, but most of the cosmic rays are gone. Maybe here's one. Um, okay, it's a much cleaner image. And this dark one is the image of short exposure, about 60 seconds. So you can see that none of the spectra really registered, and you need these long exposures in order to get the signature. So this is done. We did this. Oh yeah, I was wondering, where do cosmic rays come from? Do you know? I'll put it into our question list, which is, you know, list of questions. Okay. Um, Update the paper, make a note. Now we are having like this closing down procedure. Update. We are done. We did the combined image. So woohoo! But let's update the paper, make a note about the reduction. We did that, that it is with IRAF. Do I need to update anything on the procedure log? I don't think so, but we can highlight in green what I've done. We have done this step. Acknowledge what needs to be done and make bigger font size the next step. I guess we can go into the summary, and we have done this. We created a combined image that's free of cosmic rays. Next time we are gonna do this. Put in yellow or something. Next step. Here's our next step for video 4. I have updated the research notes, acknowledgements. What is the next step? We did this. How do we feel? We feel good, accomplished. Things are going right. Close all the windows. Yeah, let's close all our windows that are not necessary. Keep it clean. To leave a rough environment, you can type log, and then to leave the xterm exit, or hopefully you have xg term, and we can close this as well. Oh, research notes. I don't think I need to do anything else. Next step, step 5 in the procedure for Optus. Some scripts that actually terminate, and then close all of this. We can close all of this. Let me see. Anaconda can also be turned off. Off can be turned on. Not. Okay. Add two skills. So these are some to-dos for my tutorials that I will add. But great job today. We have done one important step, and I know there were many technical steps just to get to it. Um, but once you prepare everything, then really IROF is not so hard to do. You just um, it's makes a lot of the reduction steps actually easy. But I know a lot of people who don't like IROF, so maybe it's just my personal preference. But find the tools that works for you. There are many ways to do things, and maybe you have to adopt the tools that your group uses to be consistent, or you can do that and also at the same time um, uh, do the same procedure if you have time with a newer tool or another tool that you are interested in. I mean, the world is your oyster. So that you can compare and learn a new skill. Maybe your supervisor is using 100-year-old code. You want to modernize it using not uh, a different language. It's okay. And for different projects, you might choose to use different methods. It's okay. It's okay if your solution is not the fastest. It's okay if it works for you as long as it gives correct results and you can keep track of it. um, you can always improve more. That's my husband told me. You can always improve later. It's okay to do it one way. And I should get him to do a podcast with me to give us tips on coding. Um, all right, because he's the hard coder and I'm just astronomy coder. But so he can help us improve our skills. All right. Now I will be posting this on YouTube and I wish you an awesome week, awesome rest of the week. Remember to take breaks and I will try to make these tutorials shorter so that I don't have to sit here more than an hour. Okay, God bless.